Good afternoon, everyone. Welcome to your second lecture of fluid mechanics for today. Today is we're going to talk about surface tension, the second lecture. So I'm sure you guys are all happy that we're finally moving on from hydrostatics. Okay, so the fluids aren't going to be at rest for too much longer. On Monday, the fluids are going to move. So like most real fluids. But today is about surface tension. It's about a very special molecular force that in some engineering applications we have to account for. But it's a really interesting force, so I think it's going to be a really interesting lecture today. I am just going to review the key points from this morning's lecture, though, even only it was only a couple hours ago. So we did rigid body motion of hydrostatic fluid. So we started accelerating that fluid in different directions. We saw that for a linear acceleration, a constant linear acceleration, the isobars and the free surface of a fluid become angled relative to their normal non-accelerated angle. We can also rotate fluids to create parabolas, and I showed that liquid mirror telescope. So that's a special application where you can rotate, say, a big tub of mercury and then reflect light off of it to create a mirror with optical properties that you can control via the rotation speed of the liquids. Context of today's lecture. So we moved on from hydrostatics. This is another force in fluid motion, surface tension. Learning objectives are to understand what, at a molecular level, causes surface tension. We want to characterize or understand how we characterize the surface tension force at an interface. That characterization will allow us to compute a pressure differential inside a curved interface. And you'll see why there is necessarily a pressure differential when you have a curved interface. We're also going to talk about contact angle, which is the angle that a fluid makes with a surface when it's placed on it. And that creates a very important effect called capillary rise. So these are probably all new terms for you guys, but you're gonna understand it by the end of the lecture, hopefully. So I'll start off with just a nice little video. So there are some types of insects which are able to walk on the surface of water using surface tension. They're called water striders. So here's a example of a water strider here. So this is an insect that can basically exploit the surface tension force to stay on top of the liquid. There's a really good image that it's going to show here. So see it's on top, the surface tension. There's a really good image that's going to show where see how it's poking the water there? So this is water. This is, if you try and poke water, it won't do that. But this insect is able to poke water and it's like a membrane almost. So this insect isn't able to break the surface tension because of how it's evolved. So it's evolved so that its legs and feet and stuff kind of amplify the molecular effect of surface tension. And this, I guess, bug eats other bugs that drown on the surface. So that's lovely. But it works for this bug. So there's an interesting video to motivate surface tension. So let's talk now about molecular forces. So surface tension occurs at an interface, vaguely speaking. So that could be a fluid-fluid or a fluid-solid. And it's caused by cohesive molecular forces. And what these cohesive forces do is they want to pull our fluid molecules inward. So at these interfaces, cohesive molecular forces pull so they pull the molecules inward. So for example, the water molecules are attracted to other water molecules. So what does this look like? Let's say we have kind of a flat cup of water or an air-water interface. So for example, at the top of a glass of water, I'll draw the some water molecules here. So cohesive forces are a molecular scale force that pulls the water molecules towards other water molecules, and so on. So all the water molecules in this fluid, if you let the fluid go to rest, the water molecules won't be moving. These cohesive forces will sort of balance out. So they'll find like a nice equilibrium spot where they're attracted equally in all directions to all the other water molecules. Now at the surface, what happens is these molecules along the surface, they're pulled inward and towards the other water molecules on the surface. But since there's no water molecules above the surface, because there's air above the surface, that sort of unbalanced force creates a net like tension. You can think of those molecules are trying to go down and towards each other, so they're sort of pulled inwards. And so that inwards pulling creates a tension along the surface. So there's kind of a small tension force that's created here. And that force is what surface tension is. So that's basically the level of understanding that we need to understand of what produces surface tension in this course. So, sure. The attraction of surface molecules, and that attraction is inwards slash sideways, creates tension. You might remember in this course we're talking about continuums. So we don't care about what these individual molecules are doing except when they produce effects on our continuum. So let's imagine we have a continuum boundary now between air and water. Let's assume we have kind of some planar boundary like this. So it's water underneath and air on top. We're going to make, in like solid mechanics, if you want to compute, say, the shear force in a beam, you make a cut through the beam, and then you can discover the shear force in that cut. That's the same way we're going to analyze surface tension. So we're going to make a cut through a surface that has surface tension. So let's make an imaginary cut. In a planar surface. So the cut we're going to make is kind of here. So the length of the cut is going to have length L. So L is the length along this face. That cut is going to expose a force like this. So F, I'll call it F, ST for surface tension. And we make the same cut on the other side, which also has the same length L. So if we make these two cuts, in order for this to still be in equilibrium, these forces have equal and opposite magnitudes. So this is the tension force that's in our surface. So this is just like cutting a beam. You get like say a beam is under tension, you get that tension force when you cut it. We haven't made anything new here. The surface tension force is characterized by some coefficient, gamma, which is a material property, times the length of that cut. So you might think like when you cut a beam, you get a cross-sectional area. When we cut this surface, we assume it's a surface. So that's why it's just gamma times some length. So the molecules, it's literally like a molecule layer deep. So there's no cross-sectional area when you take your surface tension cut. It's just a length. You've cut a plane, so you get a length. So the F surface tension is equal to gamma times length, and gamma is like density or something like that. It's like a material property. So gamma is called the coefficient of surface tension. It's a very creative name. Um, and the units of that are newtons per meters. So it tells you you make a certain cut, you get a certain amount of force. So L is the length of edge we cut. And F acts parallel to this. Well, okay, F acts parallel to the surface. So it's a tension. That's why it's called surface tension. It's like a tension of the surface. So if you make that cut, the force is along the surface. So I guess it'd be perpendicular to the cut you make. Are there any questions about that? Okay. So that's how we characterize the surface tension force in a surface. There's an interesting effect that this creates, which is that if the interface is curved, a pressure difference is necessary to maintain equilibrium. And here is why. So let's say we make a cut in a curved, so the red is the cut that we're going to make. Actually, sorry, I've drawn that backwards. The red is the cut we're going to make in a curved interface. So that's kind of a, and that cut will expose a certain force parallel to the surface, as I mentioned there. Equal to gamma times length of the cut. So if we view this from kind of a side view, it looks something like this. So the F is parallel to the surface there. So if we make that cut and the F's parallel to the surface and this is curved, there's no way for this to be in equilibrium without a pressure force. That's because say the x direction components of this force will cancel each other out. You can say they may be equal in opposite direction. There's going to be an unbalanced vertical force that's downward. So in order for this to be in equilibrium, there has to be some sort of pressure distribution across that curved interface. So that pressure, remember pressure applies normal to a surface. So that's why the arrows are normal to the surface at every point. The x components of that pressure in this case would cancel. And so it's the y component of that normal vector times pressure times area that creates the force that balances this upwards. I'm going to give a more concrete example. But basically, when you cut a curved interface, you need that pressure difference to balance a component of the force that won't cancel itself out. So before I go there, maybe can anyone give me an example of a curved interface between two fluids? Ian? Waves. Waves? That's a good one. Yeah, waves. Any other examples? Hmm? Yeah, so I think that's called a meniscus. It forms on the top of the water. So like yeah, that curve on the top of a water. So any other examples? Okay, I'm gonna do those are all good examples and those are all curved interfaces. But I'm gonna do probably the most simple curved interface is a bubble. So let's say this is being copied as one big picture. So here's an example bubble. So there's a water droplet. So there's water inside this fluid and air outside this fluid. Here's some more examples of bubbles. So they're not always necessarily that perfect spherical shape. That if it's not a perfect spherical shape, that means there's some other force or something pushing on this bubble that has caused it to come out of that shape. So I'm going to consider this bubble of water here. Okay, so I'm going to jump back to the notes. So let's say that bubble is a sphere. And I'm going to cut this sphere across the middle section. So I'm going to make the same cut that I've been talking about when we cut an interface. So what do I get? I get this half sphere shape. Something like this. So when you make that cut, you get that half sphere shape. And the force that we've exposed, if we cut exactly at the midplane, so the force that we've exposed due to surface tension will point up like that. So these are small kind of individual components of that force. They point straight up. So you can think of that like surface tension force as kind of a distributed load because it has units of newtons per meter. So that uniform distributed load that we've cut produces a net surface tension force upward here. And now, so we have a pressure distribution, like I said, on a curved interface. So this is a curved interface. The pressure distribution on the curved interface down there looks something like this. So again, it's always normal to the surface. And the nice thing about this pressure distribution is that since the x components of that distribution cancel out, we only have the y components. And the y component acts on this cross-sectional area here. So the F pressure is something like that. So it acts on the projected area of this half sphere. The projected area of the half sphere is just a circle. So it's going to act on a circular area. Are there any questions about that before I do the math with this? Okay. So for this to be an equilibrium, we have a balance between the surface tension force and the pressure force. This pressure force is created by a differential in pressure. So we say P1 is on the outside of this bubble and P2 is on the inside. Delta P is equal to P2. So it's sort of this pressure force causes the pressure differential between the inside and the outside of this bubble. Okay, so the forces are equal to the surface tension force is gamma L, like I just set up above. And this is a straight vertical force balance, I should mention. The x direction components of the pressure distribution will cancel each other. So we only have the vertical components of that pressure distribution. Again, the force due to pressure is still pressure times area. In this case, I'm doing the differential pressure times the area. We can express all of these in terms of the radius of this bubble. So big R is the radius of this spherical bubble. And just to clarify, the L I'm doing here, this L is the circumference of the cut we've exposed. Because remember, the surface is just a surface. So we cut this and we expose some length of surface. So this is the circumference of the circle. So pi times d, or 2 pi r. Are there any questions about the geometrical quantities? The A here is the area of this whole cross section, which is just a circle. Yes, please.
I get that the magnitudes of the force, but should the vectors be like one of them should be negative since they're pointing in the opposite direction?
Yeah, so you would do, so for equilibrium, you would do, say, FST would be positive in this convention, minus FP is equal to 0. Like summation of forces is equal to MA, right? So then you could just move it over and set them equal. But good question. Any other questions? Yes, please. Yeah.
Is this equation unique to cross section at the middle or the other slice?
The equation, the last line is unique to the geometry of this bubble. So if you have, say, an elliptical bubble or a general curved interface.
No. Sphere, and you take the slice.
Yeah.
Say anywhere, like even at the very top.
Yeah, like not through the midplane. Like if you were to slice it, like here, is that what you're asking? Yeah.
The radius is 0.
But so at the top, if you were to slice it at the top, it's a good question. Your area would also be 0 that the pressure is applied over.
Yeah.
So no matter where you slice this, you'll still get the same balance, but the area of the pressure applied to will be changing. So the reason I sliced it across the middle is so I only get a y component of my surface tension force. Because say you slice this bubble here, your surface tension forces will come out like that at an angle. So that's why we're slicing it in this derivation across the midplane. Yeah, no problem. Any other questions about this? So now we can directly relate the pressure differential to the surface tension. So delta P is delta P is 2 gamma over R. So how you can think of this, the pressure differential is created by the surface tension sort of squeezing the bubble. So you're going to increase the pressure inside the bubble. And the reason that that squeeze has to happen is because the interface is curved. So there will be an unbalanced, for any cut you make, there'll be an unbalanced portion of the surface tension force. So this is for a bubble being squeezed. That's why it's squeezed by that surface tension force. The rise in pressure in the bubble will be due to that sort of compression you're putting on the bubble. Any questions about this? I'm not going to do the derivation. So this is for a spherical bubble. I guess you like assume an ideal bubble in this case. For a non-spherical bubble, something more generally a curved surface, you could define the curvature in terms of two radii of curvature. So for a general curved surface, you get this. So delta P is gamma 1 over R1 plus 1 over R2. R1 and R2 in this case are two radii of curvature. So for a sphere, the two radii of curvature are both just R. But say you had an elliptical bubble or something like that. The curvature in the two different directions is different. So the radius of curvature, those two radii are R1 and R2. If you wanted to say have like the curved interface I drew above, where it was just a plane that was curved, the radius of curvature in one of the directions would be infinity. So if you want to make R, if you set R to infinity, like the radius of curvature of something that's flat is technically infinite. You could think like this is a small radius of curvature, this one's bigger radius of curvature, and you keep going until you get infinity for a flat surface. So R is infinity is not curved. And for that bubble above, we get R1 equals R2. So that's why we got 2 gamma over R. So any questions about that? So now we can compute the pressure differential across a curved interface, knowing the surface tension, uh, that surface tension coefficient across that interface. Contact angle is another important fluid property. Let's say we have a bubble or some sort of fluid resting on a solid surface now. So you have this bubble resting on a surface. At this point, the angle that's made with the surface is actually a fluid property. So that angle is defined this way. So you can think of that angle being through the fluid. So you draw that angle through the fluid to the line tangential to the interface at the solid boundary. So that's what contact angle is. So you might have heard of like surface wetting, surface non-wetting. That's related to the contact angle. So if theta is greater than 0, or sorry, theta is greater than 90, it's called non-wetting. If theta is less than 90, it's called wetting. So the bubble will wet the surface. So that looks like, wetting looks like this. Something like that. So in this case, that angle theta is like this, right? This place. I don't know what happens if theta is 90. I guess it's existing as a wetting and non-wetting. I think in practice that would be like super rare. Like this is like a fluid property. That'd be like, what's the odds that like, yeah, if you can come up with a fluid with theta is 90, put me on the patent, please. So these are some pictures of what wetting and non-wetting fluids look like. Normally water, like if you spill water on the counter or something, it looks something like the right picture there. So that it's kind of wetting. So that's why it kind of spreads out. So that surface tension force kind of pushes it out. Yes, please. It does. Very good question. That's about what I'm about to say that. So these water droplets now on the leaf surface, in this case, are non-wetting. So you can see how the droplet, that contact angle here is basically greater than 90. So it's all of the surface tension properties, the coefficient of surface tension, the contact angle, they're all dependent on the two materials. So water, air, not water, like water versus one surface will have a different property characterizing it than water versus another surface. Yes, please. Yeah. Yep. No, the contact angle is that instantaneous. So you might think like, well, if you had a non-wetting fluid, couldn't you just make like a ginormous bubble resting on the surface? So that the contact angle is like if you zoom in to this surface, that's what the contact angle is. So it doesn't depend on the mass of the fluid. If even if like say your contact angle in water, if you have like a big thing of water and you spill it all over the counter, the surface tension is made at the intersection of the surface of your water with the geometry. So that's the contact angle. Does that kind of answer your question? It's unintuitive because you think like if I have like more fluid, wouldn't the angle like decrease or something like that, right? Yeah, exactly. Because the surface tension applies only at the surface of that pool. Exactly. Yeah, the droplet is when everything is in perfect equilibrium, then we get the droplet. But the weight, for example, in the fluid would push that droplet, turn it into like a big blob. Right. Okay. Any other questions? Oh, yes, please. Sorry.
I imagine like you're drawing right there,
Huh?
kind of like I imagine like it might like a curve, like a smooth transition eventually.
A smooth transition? Yeah, so I'm saying like if you had a big enough fluid, it would do something like this, right? But that contact angle here is the same. It's a fluid property. Does that answer your question?
Yeah.
Okay. Any other questions? Yeah. Do you have a question? Oh, sorry, Omar. I thought you were putting out. All right. Okay. Let's um let's move on to another important effect that's created by surface attention. So that's called the capillary effect. So liquid will rise or fall in a tube due to surface tension. So let's say I have some volume of water here. It doesn't even have to be water, it can just be some blue fluid. And I put a tube in there, an open-ended tube. The liquid will actually rise up that tube a small amount. So it'll do something like this. And we can compute this now using surface tension. I'll explain how. So if you define the height that it rises as some height h, and let's zoom in right at the surface of the tube. So this here on the right hand side is just a zoom in of that interface. We know that this angle here is the contact angle, theta. So it's how I defined it before was really like this angle, but we know those two angles are equal. So the reason for this rise is that the surface tension can actually support a certain weight of fluid. So the surface tension will keep pulling that fluid up the tube until those two forces are balanced. So that weight of fluid looks something like this. So this is kind of a surface tension forces along that interface will be tangential to the surface. And like your other question when I was cutting the the sphere, these forces are no longer straight vertical. They're based on the contact angle. So we know that the angle that that force makes will be the contact angle. So we're going to again do a force balance here. This is going to be a Y force balance. So the Y component of the surface tension force at the wall will be the force magnitude times cos theta, where theta is the contact angle. And that's just equal to the weight of fluid being supported. So this force balance, just to clarify, is just some force of surface tension, the Y component of that force, balanced with the weight of this fluid here, this fluid column. Again, these are all geometrical quantities that we can just compute. So the force of surface tension will be gamma 2 pi r. So 2 pi r is the circumference of this tube. That's the length of the interface. Cos theta equals rho pi r squared h times the gravity. So this is rho v. We're assuming this is, we're going to neglect a little bit of missing, I guess it depends where we define h2, but this is just the volume of a cylinder. So this is the volume of the cylinder of fluid that our surface tension force is creating. So because that contact angle, just like when you pour it on a surface, the uncancelled, so the remaining part of the surface tension force will pull that fluid and spread it out until everything's nicely balanced. This is a very special case of that, where it will actually pull it up a tube. We can get the following expression for that height. H equals gamma 2 cos theta over rho gr. So that is the height of fluid that our surface tension will support. And so this is a height that is actually observed rise in the fluid. So with a really, really big tube, you don't really notice this rise, but when the tubes start getting really small, you notice this rise, this capillary rise. And it's exploited by a lot of, like this is part of how trees get water up from the roots. You remember like capillary reaction and stuff? This is part of the reason. So I guess the xylem in the trees are very thin tubes, almost like perfect tubes, and they can exploit this capillary rise. It's one method I guess trees use to get water up from the roots. Are there any questions about this? I'm going to show some videos just so you believe me, because this sounds like I made this up, to be honest. Any other questions? No? Okay. The interesting thing about this contact angle is that if the fluid is wetting versus non-wetting, we actually don't always get a rise. We might get a fluid drop. So mercury is an example of a fluid which is non-wetting. So if you have a big thing of mercury and you stick that tube in there, you actually get the H is going to be below the surface. That's because of the contact angle of mercury. So this is theta greater than 90, so it's non-wetting. The above equation gives you that negative because cos theta is negative for theta greater than 90. But most fluids are wetting, so most practical fluids, you experience that capillary rise. So in this case, just to clarify, cos theta. So that's theta greater than 90, which means we have a non-wetting fluid. Any questions on capillary rise or fall? Oh, yes, please.
Is there a surface you could put mercury on where you'd make it wetting? Or is mercury no matter what always not?
That's a good question. To be honest, I don't know the answer because the contact angle, like I said, is a property of the fluid and the surface. So, like even water, for example, like example, you're designing a tent or designing a material that you want water to beat off of. That contact angle is super important because if it's non-wetting, like the water can roll off your like tent, for example. So that's like with the treatments that are applied on clothes and stuff like that. That's all related to surface tension, the contact angle, because that's a property of your fluid and your material. Any other questions? Okay. I'll play some videos now just to demonstrate. So this is a capillary tube demonstration. So these are a series of, I guess, tubes, and they're going to get smaller as you go from right to left. Actually, to be honest, the music in this video is pretty good, so let's play it. So the tube on the left is the thinnest. Um, so when the forces kind of balance, you get the highest capillary rise on the left tube because it's the smallest radius. What's interesting here, okay, so there's actually a balance of hydrostatic forces happening here as well. So this big tube, it gets basically no capillary rise. So that means the pressure is constant along this line. So this one rise the largest of that. So it's kind of equivalent to the way I drew it before, but there's also like a hydrostatic thing happening here. Does that make sense? So any questions about this? I'll play it just so you can. Okay. Yes? No. The pressure differential there. Yeah. So this whole rise, like you said, is a good question. So this whole thing isn't because of capillary reaction. It's just the difference between the tube on the right and those other tubes. That's because of capillary action. Any other questions? Okay. There's also a good video here um, that shows contact angle for a couple different fluids. So it's comparing, like if you compare the water to the alcohol there, you saw the alcohol kind of runs much more smoothly off. That's because of contact angle. It's probably also because of viscosity, I would guess. But so this is like what you were talking about with the meniscus. So the surface tension is basically stronger in water than it is in alcohol. So you're able to support a bigger meniscus in water versus alcohol. So that meniscus before it collapses is smaller in alcohol. They're also on them. So this he's gonna also show the mercury. So that's what mercury looks like. I don't have any liquid mercury, but you see it like rolls around. It's a very weird fluid. Um, see it kind of just rolls around on the glass. That's because it's non-wetting. So we're used to most fluids like wetting glass.